Welcome to this Java Swing project. Watch how planets orbit the Sun in this stunning solar system animation. First, we'll start by creating a new class called Solar System. Let's begin coding. Alright, let's begin by importing all the libraries we'll need for this project. We'll start with Java Swing, which helps us create the main window and handle the entire graphical interface. Next comes Java AWT, used for drawing shapes, setting colors, and handling all the visuals of our solar system. Then we import Affine Transform, an amazing class that lets us rotate and position our planets smoothly as they orbit around the Sun. Finally, we bring in Random, which we'll use to scatter tiny sparkling stars across the background, giving the animation a real space-like look and feel. Now Solar System class extends from JPanel to handle all our custom graphics. Now we set the window size, width as 950 pixels and height as 900. These constants define the area where our entire solar system will appear. Now we'll create a planet class to store all the details for each planet. It includes the name, the orbit radius represented by r, and the size of the planet. We also add speed and angle to control how fast each planet moves around the Sun. Finally, we store a color value so every planet can have its own unique look in our animation. Now let's define a constructor for our planet class. Using NetBeans insert code option, we generate it automatically to set values for each field, name, radius, size, speed, and color, except the angle, which will update later during animation. Next, we add a tick method. Each time it runs, it increases the planet's angle by its speed, making the planet rotate smoothly around the Sun. We'll create a final array of planet objects, which will hold every planet we want to animate in this project. Each planet is created using the constructor we wrote earlier, and inside the parentheses we pass its details, name, orbit radius, size, speed, and color. Let's go through each one step by step. First is Mercury, the smallest and fastest planet in our solar system. It's given an orbit radius of 70 pixels and a size of 6. Its speed is set to 0.055, which makes it revolve quickly around the Sun. For its color, we're using a grayish tone made from RGB values 180, 170, and 160. Next is Venus. It's slightly farther away, with a radius of 110 pixels, and a size of 10. The speed is 0.040, so it moves a little slower than Mercury. We color it with warm yellow-brown shades, 206, 178, and 120, giving it that golden Venus look. Then comes Earth, our home planet. Its orbit radius is 150, size 10, and speed 0.035. We've chosen a blue color, 90, 140, 255, to represent the oceans and atmosphere. Moving outward, we have Mars, the red planet. It has an orbit radius of 185 pixels, a smaller size of 8, and a speed of 0.030. The color is a reddish tone made from 220, 110, and 90, giving Mars that warm desert look. Next up is Jupiter, the giant of our solar system. Its radius is 250, size 18, and speed 0.020, since the outer planets move slower. We color it with beige-brown shades, 220, 190, 150, to capture its cloudy appearance. After that comes Saturn, famous for its rings. It's set at 310 pixels from the center, with a size of 16, and a speed of 0.017. Its color is pale gold, 220, 200, 140, matching the tone of Saturn's atmosphere. Then we define Uranus, a bluish-green planet with an orbit radius of 360, a size of 12, and a slower speed of 0.014. Its color values are 160, 200, 220, creating a light icy blue effect. Finally, we have Neptune, the farthest planet in our system. It orbits at a distance of 410 pixels, has a size of 12, and moves at a calm speed of 0.012. The color we use here, 120, 150, 240, gives it a deep cool blue tone. Next, we'll define the center point of our solar system. Here, we create a new point object called center, which is placed right in the middle of the window, using half the width and half the height, slightly moved up by 60 pixels to balance the view. Then we declare a two-dimensional array named stars, which will later store random coordinates for tiny stars in the background, adding that realistic space effect. Now let's create a method called GenStars, short for Generate Stars. This method will fill our background with small, randomly placed stars to make the scene look more realistic. It takes three parameters: the total number of stars, and the width and height of the window area. Inside, we create a random object that helps generate different values each time. We then build a two-dimensional array where each row represents one star. The first two values in every row are the x and y coordinates, showing where the star will appear on the screen. The third value defines the star size, which we set randomly to either 1 or 2 pixels for a nice variation. Finally, the method returns this array, giving us a sky full of stars that stay consistent each time the animation runs. Now we'll define the constructor for our solar system class. This is where everything gets initialized. First, we set the background color to a dark navy shade, giving it that deep space look. Next, we call our GenStars method to generate 220 random stars across the window, which adds life to the background. Then, we create a timer that updates the animation about every 16 milliseconds, roughly 60 frames per second. Inside the timer, we loop through each planet and call its take method to update its angle and position. Finally, we call repaint to redraw the entire scene continuously, creating smooth orbital motion for all the planets. Once the timer starts, our solar system begins to move in real time. Now let's move on to the paint component method. This is where we actually draw everything on the screen. We start by calling super.paint component, which clears the previous frame before drawing the next one. Then we create a graphics 2D object from the base graphics reference, allowing us to use more advanced drawing features. Next, we enable anti-aliasing to smooth out the edges of circles and lines, giving our planets, orbits, and stars a much cleaner and more polished look. Next, we'll draw all the tiny stars in our background. First, we set the drawing color to a soft bluish-white using RGB values 230, 230, 255, giving a subtle glowing effect. Then, using a simple for each loop, we go through every star inside our two-dimensional array. For each one, we draw a small circle using fill oval, based on its x and y position and the size value we generated earlier. Together, these hundreds of little dots form a calm, starry night sky behind our solar system. Now we'll draw the orbit paths for each planet. We start by setting the stroke width to just 1 pixel using basic stroke, which keeps the orbit lines thin and clean. Next, we set the color to a soft white with low transparency. The fourth value, 40, makes the orbits appear faint and realistic. Then, inside A for each loop, we go through every planet in our array. For each one, we calculate the orbit's diameter and draw a perfect circle around the center point. This gives us the circular paths that each planet will follow as they revolve around the Sun. Now it's time to draw the Sun at the center of our solar system. We start by setting the Sun size to 36 pixels, which defines its overall radius. Then we create a gradient paint that smoothly blends two warm colors, a light yellow at the top left and a deeper orange toward the bottom right. This gradient gives the Sun a glowing, realistic appearance instead of a flat circle. Finally, we apply the gradient using set paint, and draw the Sun itself with fill oval, positioning it perfectly in the center of our window. Before drawing the planet names, we set the font style using sans serif with a plain weight and size 14. This keeps the text clean, simple, and easy to read beside each planet. Now we'll draw each planet in motion. Inside A for each loop, we calculate the current position of every planet using trigonometric functions, cosine for the x-axis and sine for the y-axis. By multiplying each planet's orbit radius with these values, we get smooth circular motion around the center. Then we set the drawing color to the planet's specific color and use fill oval to draw the planet as a small circle at that position. As the angle keeps updating in the timer, each planet will move along its orbit, creating realistic rotation around the Sun. Now, let's give Saturn its iconic ring. We start with a simple if condition to check if the current planet's name equals Saturn. Then, we set a light golden color with a bit of transparency, using RGB values to make the ring look soft and glowing. Next, we save the current transformation state of the graphics object, and move the drawing position to Saturn's exact coordinates using Translate. We then apply a small rotation of -0.6 radians to tilt the ring slightly, giving it a 3D look. Finally, we draw an oval that wraps around Saturn and restore the original transformation, so the rotation only affects the ring, not the rest of the scene. This simple trick makes Saturn stand out beautifully in our solar system animation. Now, we'll draw the labels for each planet. We start by setting the text color to a bright gray, RGB 240, 240, 240, so it stands out clearly against the dark space background. Next, we calculate the label's X and Y positions by offsetting them slightly away from the planet's orbit. This small adjustment keeps the text from overlapping with the planet itself, even as it moves. Finally, we use drawstring to display each planet's name right beside its position, making the entire solar system easy to follow visually. Finally, let's wrap everything up with our main method, which launches the solar system program. Here, we use invoke later. This ensures that all the graphical code runs safely on the event dispatch thread, which is the recommended way to start any Java Swing application. Inside the runnable, we create a new JFrame and set its title to Solar System Model. Next, we specify the default close operation as exit on close, so the application shuts down properly when we close the window. Then, we set the frame size using the constants W and H that we defined earlier, ensuring the window fits our design perfectly. The line set location relative to null centers the window nicely on the screen for a balanced look, and set resizable false locks the size so users can't stretch or distort the layout. After that, we add a new instance of our solar system panel. That's the component that handles all the drawing and animation we've built so far. Finally, we call setVisibleTrue, which displays the window on screen. Once this runs, you'll see your complete solar system model come to life, planets orbiting, stars twinkling, and everything running smoothly through Java Swing. And that's it, our solar system animation in Java Swing is complete. We built planets, orbits, and smooth motion all from scratch. If you enjoyed this project, don't forget to like, share, and subscribe for more awesome Java animations and coding tutorials.